If we provide more energy to a system, we've seen through the equipartition principle that we occupy higher and higher level quantum states, such as translations, rotations, and vibrations. But how is this energy related to the temperature of the system? Remember that we've defined temperature as the partial derivative of energy with respect to entropy at constant volume. And so temperature has to do with how fast the number of microstates increases as we increase the energy. Let's look at our energy level diagram again, and let's blow up a little tiny slice of energy and look at the translational states in that small slice of energy. You can see that for a very small increase in energy, we drastically increase the number of microstates, making the temperature large. If we look at rotations, remember that each rotational state is 2j plus 1 degenerate, so this first rotational state, j equals 0, has one way to make that state. There's one microstate there. J equals 1 has 3 microstates, and j equals 2 has 5 microstates. So again, the number of microstates increases fairly rapidly as we increase the energy, giving that a large effect on the temperature. However, for vibrations, in that same small amount of energy, we can't even excite one vibration. And so vibrations are not easily excited states and don't contribute much to the temperature because we don't increase the number of microstates until we can excite higher level excited state vibrations. So translations and rotations have the largest effect on the temperature of our system. Using a similar argument, changing the potential energy of a system does not typically change the number of microstates by much, and therefore potential energy does not affect the temperature of the system. Since translations have the largest effect on the temperature, let's take a look at the distribution of translational energies, or the distribution of velocities in the system, and see how that's related to the temperature. This will lead us to our Maxwell-Boltzmann distribution, which we introduced in Chapter 1. Since the translational energies will be in a Boltzmann distribution, we can use the Boltzmann probability distribution to express the probability distribution of velocities using 1/2 mv squared as the energy of each velocity state. The appropriate normalization constant or partition function would be the translational partition function. Substituting in for that translational partition function, we arrive at the following velocity distribution. Since the velocity of a particle is the same in all directions, we can integrate over all angles to give us the speed distribution. Remembering that the volume element in spherical coordinates is v squared sine theta dv d theta d phi, and that the angle phi ranges from 0 to 2 pi, and the angle theta ranges from 0 to pi, we can substitute our velocity distribution into this integral, evaluate the integral, and obtain the following speed distribution, which you will recognize as the Maxwell-Boltzmann distribution from Chapter 1.